Welcome back to the week 2 of the course Machine Learning 1, Understanding the Foundations of Pattern Recognition and Machine Learning. My name is Deepak Gupta and I am an adjunct professor at the TechSmin Hub, IIT Dhanbad. This course is a part of the skill development program launched by the TechSmin Hub at the Institute and has been built with the joint efforts of IIT Dhanbad, Transmute AI Lab and TechSmin Hub. In this week, we are going to discuss two modules. First, we will discuss what pattern recognition means. In the second module, we are going to provide an overview of the probability theory. Both the concepts are very important for the field of machine learning. Moving to the first module, pattern recognition. So, what is pattern recognition? As the name sounds, it just refers to identification of the patterns and the regularities in the given data. Data can be very rich, but if we do not have good algorithms or good approaches to extract those patterns from the data, that data is pure waste. So, pattern recognition refers to the set of algorithms which can be used to derive information from the data. A very good and very elegant example of pattern recognition is the empirical laws of planetary motion derived by Kepler. We know Kepler for these planetary motion laws, but did you know these astronomical observations were from Tycho Brahe? It was Kepler who, in the 16th century, analyzed the data and came up with the empirical laws of the planetary motion. So, today these laws are very important to understand configuration of the planets. It wasn't really too much physics-based models. It was basically the information derived from the data. So, data can be very important for certain cases. Now, coming to a very simple example of pattern recognition. On the left here, we see the MNIST digits. These are very popular digits. And let's say if we want to build a machine learning system that can classify these MNIST digits. One of the simple ways to build such an ML system would be to feed handcrafted features to our ML system. For example, in this case, we can come up with a system that differentiates 8 and 1 based on circles and straight lines. It differentiates 7 and 1 based on that 1 has one straight line, 7 has two straight lines. Similarly, we can come up with a lot of geometrical features that are able to separate those 10 digits. It sounds a bit difficult, but it's not impossible. So we can design an ML system using handcrafted features to differentiate all the 10 digits in the MNIST set of digits. That would be one approach to build an ML model. Another strategy could be to rather building handcraft features, feeding a lot of label data. So labeling this as 8, 8, 1, 5, 1, a lot of labeled samples and giving it to a model, and the model learns end to end based on the data what important features are that characterize each of the classes, and then it builds a ML model. That can be one approach. So on the top we have handcrafted features, on the bottom we have features which are directly derived from the data. This is not typically a ML model, this would be just a traditional classification model. Now what the idea is that this one on the top, this is not a data hungry model. You don't really need to give it a lot of data during the training time. This one, you need to give a lot of data during training time, but then it has its own advantages. We'll see another example. Now, understanding the bridge between pattern recognition and machine learning. In the previous example, we saw that this example, we saw that we could come up with handcrafted features. Although we don't show the handcrafted features, intuitively we can understand that we can come up with features like straight lines, curves, circles to differentiate the 10 MNIST digits. It's hard but doable to manually design a classifier. But what about this case? We have a cat and we have a dog. Can we easily design these, come up with simple features like lines, curves, or circles that can differentiate the two? There can always be more samples of dogs which look visually as similar, very similar to these cats. So it's not easy to come up with those manual features. In this case, we don't have the choice of building handcrafted features, and we have to rely on the data. It's super hard to identify features using the standard processing techniques. That is where machine learning comes to safety. Now, what's important for a pattern recognition system? It is easy and quick in terms of recognizing the familiar patterns. So if we're building a pattern recognition system manually, and if we have this type of a data, I don't think we can really come up with features that can recognize each of these samples. Now, another important characteristic of pattern recognition is that it should be able to relate and classify unfamiliar objects. We don't want the model to learn only the digits that we show it or the only pictures of the dog or cat that we show, but it should also be able to relate and classify pictures of dogs which are similar to this one, or at least in a close proximity. So we want our model to generalize. Third, these should be robust to noisy conditions. If we are able to characterize this dog in a very clean condition, we also want our model to be able to identify the picture of dog in difficult conditions as well. These three basically form the important characteristics of our pattern recognition system. So now we said that we could derive these patterns in a data-driven manner, but can we really do that? We start with a very simple example of regression. This example we showed in one of the slides from the previous week. What we see here is that there's an underlying model, sine curve, which is shown in green. From the sine curve, we sample a few data samples, which are shown in blue circles. And what we want is that assuming that we don't know the green curve now, we want to build a model, a regression model, that can approximate the green curve as much as possible. Note that it is important to note that we do not really want to fit the model perfectly on the blue circles. We want the model to fit on the green curve for a better generalization. Here we have 4 different values of m, and m corresponds to the order of the polynomial that we choose for fitting in the data. With m equal to 0, we see we fit a horizontal line, but then if we look at the deviation of each of these circles or the corresponding green point from the line, it's quite far. So there's a lot of error here. When we increase the flexibility of the model with first order polynomial, we see that the error has relatively reduced. When we go to m equal to 3, we see the model fits very well the green curve. There is still some error, but then with m equal to 3, that's the best it can do. With m equal to 9, what starts happening is that our model is chosen model is fitting perfectly the data samples, but not the underlying model. This implies that it is fitting the model plus noise. But what we don't want our pattern recognition system is to learn the noise. What we want it to do is to understand the underlying pattern of the model only. So in this case, what we saw was with different choices of the model complexity, we identify the underlying pattern in the data. But it is very important that the model complexity is also chosen properly. That's what we can infer from this case. If we choose too complex model and we have very limited data, we end up with identifying patterns which are not the reality. We are going on learning the noise. So it is important that when we are learning the pattern from the data, the complexity of the model is chosen properly. Now, this is an example of a popular deep learning case. We are not going to discuss in details the deep learning method here, but what I would like to show you here is that with the deep learning model, if we want to, for example, build a classifier for identifying this picture, whether it's a car or not, with the deep learning model, it is possible to identify the underlying patterns at different levels of the feature complexity. For example, here we have low level features, then we have mid level features, we have high level features, and deep learning models can combine these features from different levels to build very strong classifiers. What I want to tell here is that these patterns that we see, we cannot build them in a handcrafted manner. We cannot come up with these patterns manually. Even if we are able to do that for 1 or 2 examples, it is impossible to build such pattern recognition systems for a very generalized set of cars. Let's say we have 10,000 cars, we cannot really go on building these patterns one by one. But the power of deep learning allows to build a very generalized model that can identify these patterns. That is what we can say in terms of doing pattern recognition in a data-driven manner. Now, apart from the model complexity that we saw, what is the importance of the data for a pattern recognition system? As it sounds, I mean, if the model is data driven, then of course, for the pattern recognition system to work, well, you need the data. But how does really the amount of data impact your pattern recognition system? This we can see from two examples here. Here, n denotes the number of samples. We again have the green curve, and we have blue circles, which are samples with noise sampled from the curve. And in this case, we have n equal to 100 samples. In the left one, what we see is that for a certain order polynomial, I'm not sure which order polynomial was chosen here, but I think it might be, let's say, sixth order polynomial. Let's say sixth order polynomial. If we choose a sixth order polynomial, we see that the model starts learning the noise, right? We see that it shifts away from the green curve. It tries to fit as many blue circles as possible. But if we increase the amount of data, we see that even with higher complexity model, we are able to identify the underlying pattern very well. What this implies is that irrespective of the complexity, or I wouldn't say irrespective, but if we have sufficient data, we do not have to fine tune the complexity of the model. That is the importance of data in a pattern recognition system. I guess this is all that we have to learn about pattern recognition. The last message for this slide was, for higher order model complexity, more data is needed to accurately identify the patterns. Thank you.